Thank you for joining us today and sharing all your learnings. We have a lot of questions that have come in, so let's get started and try to cover as much as possible today. So the first question, Rohit, it's for you. Your talk touched upon different network topologies for large-scale training. Can you share your thoughts on how EOR, TOR, and rail-based topologies compare in terms of scalability, latency, and tolerance, and what are the trade-offs in choosing one over the other?
Sure. Yeah, it's a pretty loaded question. I mean, it depends on completely on the use case. End of the row obviously has its some benefits in terms of lower latencies because you have lesser hops you can do, and generally beneficial for smaller scale GPUs. For example, if you're doing recommendation models and so on, where you need maybe 100 GPUs, 200 GPUs kind of, and you will have very less latency. They're more latency sensitive workloads. But for GenAI kind of use cases, you obviously will go across the hops, so it's maybe not as important. But the other things start to play a role, such as the reliability, the failure domains. Generally, when we run big scale models, we need to have backup capacity for in terms of failures. And in case of end of the row, the failure domain is high, so we need more capacity as a backup. And then there is a lot of maintenance issues with it in terms of optics and links going down and stuff like that. So I would say it's overall depends on the use case to use case kind of thing. But for higher scale, we obviously need to look at non-EOR topologies.
Yeah, thank you. Thank you. It's not a straightforward way to decide. Loaded question, loaded answer as well. David, there is a question on OCI. For GPU-heavy RDMA workloads like the CFD simulations in HPC compute or large AI model training, how does OCI's backbone architecture and inter-region RDMA implementation maintain this bandwidth consistency at scale?
So that's a good question. We don't actually support long distance RDMA at this point. We're working on doing campus-wide RDMA, but we don't have anything that prohibits RDMA packets going over the front side network or between data centers, but we don't have anything that actively supports it. All the ECN marking, that sort of support, it just isn't there on the front side network.
Excellent. Thank you. The next question also seems to be to you. You touched a little on optical link flaps. The question is, how significant are the optical link flaps in large-scale networks, and are the strategies deployed good enough to achieve the stability we need for AI workloads?
We put a lot of work into addressing our link flap issues that we've seen, and we've attacked it from all levels. Like I talked about working with our vendors, we've tried to do debouncing. We work with DSP vendors to figure out why they're flapping. And we even work with the higher level NCCL level. They'll look at link flaps, and NCCL can automatically switch. Where in future versions of NCCL, hopefully we'll be able to have a software level solution.
Sounds good. There seems to be a lot of interest in optical link flaps. Ankur, a question on DSF for it. As you expand DSF fabric to multiple buildings and beyond, do you see a risk of optical link flaps at longer distances? And what mitigation strategies does Meta have in place?
Yeah, I think optics failure and the link flags is probably the most common type of failures which all type of networks see. And for DSF, the good thing is that the detection time in the link failure is pretty quick. It's less than 1 millisecond. And this is done because we exchange these DSF reachability cells between the links, and which can propagate to the entire end-to-end in less than a millisecond. So this is within a DSF fabric zone. And if I have to compare it with front-end network, where we use ECMP pretty heavily, the link scan time is in order of around 12 milliseconds. So it takes somewhere between 12 to 25 milliseconds to remove that member. So DSF has a big advantage here. But for long distance, another part of question when the network size grow. So let's say there is a failure in a remote zone, remote AI zone, and we are combining multiple DSF AI zones via dual stage spine. And as Ron mentioned, the input balance feature kicks in, and that avoids the funneling effect. And as I mentioned, that within a millisecond, the reachability information is already propagated, and the bad element is removed from the forwarding path. One tricky part is that when there is a DSF to IP interconnect. So there we run BGP, and if let's say we had to, only rely on the BGP, then it would be in a matter of seconds. However, we have developed a feature for the edge, which is called like second chance CCMP, where even if there is a link failure, we hash on to the backup path. And let's say primary and secondary both failed. So again, within a millisecond, the DSF ingress node would know about the failure and remove it from the next hop. So I think we got it covered there, but we also have a proactive monitoring, like monitoring prefab BER and factails, which helps us identify the links before they actually flap. I'm sure you cannot catch everything, but whatever we catch is good there. So that's and we have a self-healing, pretty good self-healing. If there is a repeated offender, it gets removed from the forwarding path by the tooling here.
Cool. Thank you. Thank you. Hani, this question is for you. What are the trade-offs of using ATSW mesh versus going up with another super spine layers above the ATSWs?
Yes. Yeah, this is definitely one choice in network design that is critical in different ways. So if we choose to deploy another super spine tier to interconnect clusters, then there is definitely additional hub that gets added, and there is latency through the packet processing pipeline of that new hub. Particularly if we use deep buffer switches under congestion, that latency can be significant. So that's one consideration that we look into when adding additional network hubs, right? On the other hand, connecting directly in a full mesh also makes your bandwidth static, right? You have more flexibility for sure when you have another tier of network that can switch bandwidths between any pairs of buildings on demand.
Cool, thank you. Ron, a question on cellification for DSF. Could you describe how cells are defined, and how does this DSF credit-based congestion control differ from PFC or ECN used elsewhere?
Yeah, so I think the cells are actually, it's kind of like a special protocol that breaks a packet into smaller cells. And then we append some sort of like DSF control protocol header within the cell. And that will spread across the network. Where in the destination RDSW, when it's reassembling the cells, they can look at the header, understanding what are the sequence of these cells, and then reassemble into a full packet, handed back to the IP layer. For the second question, in terms of PFC and credit-based congestion control, they're actually both playing the role in congestion control in the DSM network. In the IP layer, we utilize PFC to back pressure the sender. That back pressure will forward towards DSF as in congestion control, credit-based congestion control. That when it goes through the spine layer, it will go back to PFC again. Imagine that goes to the other side of DSF network, also coming back to credit-based congestion control. So they're kind of like interoperating with each other in the DSF network, such that we have a non-blocking domain within the entire DSF network.
Perfect. So while we are on this PFC topic, David, a question for you. In the OCI network, can you explain the rationale for avoiding end-to-end PFC? And do you run into any situations when ECN alone is not effective enough?
So for PFC, like we mentioned, and other speakers have mentioned, there is a head-of-line blocking problem. And we have the multi-tenant problem. We don't want different tenants triggering PFCs that block other tenants' traffic. So that's why we don't do widespread PFC throughout the network. So for ECNs, we are hoping that ECNs is tightly tied to DCQCN. That's our main congestion control process historically. We're hoping for new solutions to congestion control, packet spraying, RTTCC, which is round trip time congestion control, and those won't depend on ECNs at all. So at that, well, they can use ECNs, but they don't need ECNs. So we're hoping that ECNs can go away in the future.
All right. Sounds good. Rohit, probably you could take this question. In your talk, there was a mention of undersubscription at RTSW, while ATSW is oversubscribed. What factors determine undersubscription, oversubscription ratios in AI clusters, and what are its practical impacts?
Got it. Yeah, I think that's a great question. It's an engineering trade-off. Basically, if you look at from the model perspective, they will get the maximum throughput running within the zone or very close to each other. We would not want to send a lot of traffic far distances or long distances away. So what that kind of culminates into from the network perspective is that you're using a lot of the bandwidth inside the zone rather than cross zone. In fact, you may not even be using half of it. So that gives us kind of a flexibility to lower down the number of links that we have on these higher layers. Further, these spine switches that we put are deep buffer switches. So even if there is a buildup of congestion that happens because of more link failures or more traffic coming through them, they can absorb them better. Unlike on the slower layers where RTSWs kind of cannot absorb too much of it. So just comes down to kind of the traffic patterns that we observe and kind of the architecture we use.
Good. Thank you. Thank you. Ankur, you did talk about different collectives and the performance tuning that was done for DSF. What were some of the challenges in achieving roofline performance across different AI workloads within DSF fabric? And did you run into any bottlenecks as cluster sizes grew?
Yeah. I think there are a lot of factors which play into the tuning of a fabric to achieve the best performance, but I can talk about two main ones. So one of it is like the topology, like others mentioned here about top of the rack and end of the row rail optimized topology. And the next one is the GPU types. So when we were tuning the fabric for single stage DSF, which is non-Gen AI application, it was with H100 GPUs, we noticed that if we let the switch buffer, we are using debuffer switches, RDSW as a debuffer. If we let it buffer a lot, then it slams the DRAM pretty hard. And that is because of a shorter RTT of closely connected links. And in that case, it was better to push back on a host a little bit sooner, right, to avoid this problem. Now, we tuned it. And then we carry forwarded the same settings in the Gen AI network because that's also rail optimized, but it did not work. So what was the difference here? The GPUs. So the new GPUs, they present a new type of a bus pattern. And in that case, we noticed that we were pausing the host like 20% of the time. So then we had to change the buffer settings and PFC threshold such that, we minimize the PFC which we send toward the host, and then it achieves, the best performance. I think there was a question about the size of the network.
Yeah, do you run into any bottlenecks as cluster size?
Yeah. So I think when size of the network grow, it results into the RTT, the increased RTT between the endpoints because DSF is scheduled, right? So it has to ask for the credits. So there are some profiles, credit profiles, which we use for shorter length as well as longer distance links there, right? So we tune those credit profiles such that we do not underrun or overcommit, right? Which would end up into the packet loss problems. So we had to do some tuning there. And some of the challenge is actually, getting large scale GPUs to test. Some of the problems does show up only in production because of large scale. Yeah.
Ron, there is a question on, does input balance mode introduce any trade-offs?
Yeah, I think one of the interesting things we found is how do we make it fair to all the GPU hosts and all the network? Because link failure could occur. Link failure could occur. Input balance mode will pick which link to penalize reachability. If we do not do that properly, it will end up over penalizing some of the GPU hosts, which causing funneling again in the network. So tuning what type of penalization we do across the network would be one of the interesting challenges. It takes several iterations to see we randomize it in the fabric layer, but not randomize in the spine layer, which is unfair to the network devices, but eventually fair to the GPU host.
Correct. Makes sense. Thank you. Thank you. So, David, I think this question is for you. There was a mention of AI use cases willing to trade latency for scale. What are the trade-offs made in OCI, scale versus latency, and what is the scale of latency-limited cluster islands for customers?
Well, for latency minimizing clusters, our scale is still around 2,000 nodes. That's our two-tier networks. We're coming up with new designs that will have a higher scale, but the scales like we use for the HPC and for the X-data use cases are still in the 2,000 node area. For the other part was GPU latency.
Yeah.
So for there, we tolerate more latency, and that depends. If the customer is buying the entire building or entire campus, we do whatever latency requirements they specifically have. For our general commercial GPU latency use cases, we do try to limit the lengths of our cables and the maximum number of hops that the traffic can take to keep the latency reasonable within the actually distances be like one-way distances of 45 meters, something like that. Not that long. So per hop, so you can get multiple tiers. And the last tier we allow to be longer between the spines and the super spines.
Cool. Rohit, there is a question on what are the key bottlenecks when training large models on a cluster from GPU compute, memory, and network point of view?
Yeah, I think there are bottlenecks. Obviously, there is room for improvement in all areas. Obviously, based upon the use case and what kind of parallelisms are being used, we tend to maybe be more bottlenecked on the GPU resources, memory or compute. Like we could do more communication or network overlaps, which kind of hide the problems that network can pose. But there are some parallelisms in some of the GenAI use cases where there is less of the overlap, especially the long distances that we get exposed to. So there the network becomes kind of a bottleneck. Overall, I think there's room for improvement everywhere. We see PFCs, queue buildups, and congestion happen in the network. So that's our scope of kind of reducing those things out. And obviously, how you tune the models to have that ratio of communication to compute overlaps kind of determines how important role it plays. So that's...
All right, thank you. There are more questions on optical link flaps, which I will pass, but feel free to reach out to David for learning more about the innovations. Hani, a question to you. Which control plane protocols are used in this backend network at Meta?
Yeah, we use BGP. We use both flavors, iBGP and eBGP, in different parts of the network. Obviously, BGP has advantages that makes it attractive in large scale. Its scalability, for sure. Being a path vector protocol, it doesn't maintain a whole topological view of the entire network, so it scales well with the large counts of prefixes. Yes, the other thing about BGP is that it has fine control of policy. So it gives us actually the control that we need to manage the propagation of prefixes, where and to what limit. And we use it in drains as well. So it gives us the control that we need to manage routing in our networks. Yeah.
All right. There's still questions flowing in, but Ankur, maybe this can be our last question before we wrap up. How does DSF handle when destination RDSW doesn't have enough credits? And what are the challenges in getting this credit-based congestion control correct?
Yeah. So this is a situation where a request has been made for the credit and the egress does not have. Ideally, it should not happen because at the egress, the scheduling is round robin. So if it's, let's say there are multiple ingress which is trying to get the credit, they should at least get some and keep the queue moving. But let's say for some reason, if the ingress never got any credit back, at first it will try to push back towards the host because it has to now buffer all the packets. And there is a timeout. There is a queue watchdog timeout. If credit does not arrive in that time, the packets would get flushed to save on the resources. And what was the other part, Srilakshmi?
What are the challenges in getting this congestion control correct?
I see. So for congestion control, as I touched upon earlier, there are different credit profiles, right, which we have to tune such that we do not underrun the bandwidth or not be super aggressive. And both have the trade-offs, right? For example, if we have to tune it for latency because different collectives have different requirements. So if you assign more credits at the ingress to optimize for the latency, it has a chance that you can run into packet drops for a bandwidth intensive collective like all-to-all. So you have to make a balance there. So that is what we do by editing those profiles to make all the pieces work together, combined so that we get the perfect tuning all around.
All right, thank you. That wraps our Q&A. I don't want to keep you guys waiting for lunch. Thank you all for all the questions, for making it so interactive and engaging. Thank you to all the panelists for all your insightful answers. We will now break for lunch. You'll see directions as you step out. Thank you, everyone.